Welcome back, and we're going to start talking about the second of our gas laws that starts to explain our gas behavior mathematically. And this time we're going to talk about Charles' law, and which is the relationship between volume and temperature. So this relationship of temperature and volume, we need to remember that again we have a constant mole. So the mole is constant, so we're not changing the amount of gas. And in this case, because it's temperature and volume, we are also going to have to make sure that pressure is constant. Okay, as I said with Boyle's law, whenever we're talking about the gas laws, we need to consider which ones are going to be kept constant and which ones are the ones we are changing. And in the case of these ones, it's only ever 2 volt. We've got an independent variable and a dependent variable. So let's have a look at our simulation again. This time remembering that we're going to keep pressure constant. We're going to be changing volume with temperature. So in this case, we're not going to lock our volume. If we cool it down, we will see that our volume decreases. And if we heat it up, our volume will increase. As we cool it down, our volume decreases. So in this case, higher temperature, higher volume. Cooler temperature, smaller volume. So unlike Boyle's law, which was inversely proportional, we should see with this one that these are actually directly proportional. Just note here that we do have a temperature not in the Celsius scale. We're changing our temperature in Kelvin, and we will talk about that in just a little bit. So if we go back to Charles' law and talking about Charles' law and how we're going to define this mathematically, hopefully you will remember that with Boyle's law it was an inverse relationship, so we saw a negative gradient. This time we're going to be seeing something different. So Charles was a French physicist, Jacques Charles, and he discovered this relationship, interestingly due to his love and participation in ballooning. And if you think about this, using hot air ballooning, we're using gas, we're heating the gas with a flame, which will cause the balloon to expand. So the volume of the balloon expands. As it does so, it then lifts up into the air. So this was more than a century after Boyle's initial findings with pressure and volume relationship that we're starting to see this volume and temperature relationship. A note on temperature, when we looked at the simulations, you should have noticed that our temperature was in Kelvin, not Celsius. Now this is very important for gases, and some of you may be aware of the Kelvin scale and some of you may not. Essentially, the Kelvin relates to the absolute temperature scale, and the proportionality of Charles's law only holds true, that is, that direct relationship, only holds true if there can be a temperature at which a gas will have a volume of 0. So if we were to plot Charles's law of volume versus temperature, we would initially actually see what we have here. This volume and temperature, and the y-intercept here is well above 0. If we extrapolate this experimental data back, what we will see is that they will all come to the same intercept at the x-axis, which is equal to negative 273.15 Celsius. That point is defined as absolute 0. Okay, so the point at which we extrapolate our data back to where the gas has 0 volume, okay, so we have 0 volume, that temperature corresponds to negative 273.15 Celsius. That is equal to 0 Kelvin. So the Kelvin and the Celsius scale have exactly the same size between each degree. So 1 Kelvin is equal to 1 degree C, but they're offset by their start point. So Celsius 0 is at the freezing point of water. Okay, 0 is defined as the freezing point of water, whereas absolute 0 is the theoretical temperature, okay, where all movement stops. We've got no kinetic energy, okay, that an ideal gas will have a volume, gas has a volume of 0. Okay, so that means that anytime we are dealing with gases, we need to ensure that we convert all our temperatures to Kelvin, which we do by having the temperature in Kelvin is equal to the temperature in degrees C plus 273.15. So if we look at that, 100 degrees C is going to equal, in Kelvin, is going to be 100 plus 273.15, so it's going to be 373.15 Kelvin. Not degrees Kelvin, it's just Kelvin. Okay, so anytime we want to convert from degrees Celsius into Kelvin, we add 273. So this is just showing us the graphical representation of Charles's law. This is where our experimental data ends, and then the extrapolation back to absolute 0. We can see from this that we have this direct proportionality, that V is directly proportional, and that's what this symbol here means. It means directly proportional, which means as one goes up, the other goes up as well, okay, giving us this y equals mx plus c equation for a straight line. Okay, so if we were to take v and divide by t, we will get a constant value. So Charles's law, putting it into an equation, okay, at low volumes we have low temperatures. At high temperatures we will have high volumes. So it is for the same amount of mass, so N is constant, and our P is constant, because we are looking at changing V and T. And remember, it's proportional only to the Kelvin scale. So if we alter the conditions of temperature and volume, then what we get is this V1 T1, V2 T2, taking exactly the same form as Boyle's law, but this time, because Charles is the relationship between volume and temperature, we get the V1 T1 over V2 T2. So remember, Boyle was P1 V1 equals P2 V2. This is because of the inverse relationship. Charles is going to have our V1 over T1 is equal to V2 over T2. So this time we're doing a division rather than a multiplication. Important to remember. Let's have a look at a couple of examples. Okay, we're back to our balloon, okay, which is a common thing for gases, because if we're in a balloon, we know that there's no gas coming in or coming out. We have a fixed amount of gas. So anytime we see a balloon, we can think to ourselves, we have a fixed amount of gas. N is not changing. Okay, so N is constant, which, remember, we have to keep a track of anytime we do a gas question. So this balloon has been inflated outside on a hot day when the temperature is 40 degrees C. It has a volume of 5 decimeters cubed. So we have a balloon that is at 40 degrees C and has a volume equal to 5 decimeters cubed. We are then going to take the balloon inside into a cold store, and it's going to go into a cold store at 5 degrees, not 50, 5 degrees C, and we need to find out the pressure and the amount of gases remaining constant, so we need to find the new volume. Okay, first things first that should be ringing alarm bells here is that we have our temperatures in Celsius. So we need to add 273 to these, and we will get 40. That will be 313 Kelvin. Okay, and then again adding 273 to this, it'll be 278 Kelvin. So when we substitute in, we remember that we have T1 over V1 is equal to T2 over V2. Okay, so this one, whoops, got it upside down. Let's try that again. V1 over T1 equals V2 over T2. Remember, you should be making yourselves a formula sheet just so that you can always double check those formulas, like I did by checking back here. I had gotten it upside down. So make a formula sheet and keep it with you as a ready reference so you can always check and see if you've got your formulas upside down and if you're using the right ones. So now our volume doesn't matter as long as we're reporting in the same and it's in liters. So we've got 5 decimeters cubed divided by T1, which is now 313, is equal to X, which we're looking for, V2, over T2, which is 278. So we're going to take that and we're going to get 5 divided by 313. Okay, and we're going to multiply by 278. So we're going to get V2 is going to equal to 4.44 decimeters cubed. Double check and see if that makes sense. So what we've done is we've taken a balloon from a hot temperature into a cold temperature, and our volume has gone from 5 decimeters cubed to 4.4 decimeters cubed. So our volume has gone down, and that makes sense according to what we should understand. If our temperature goes down, our volume should go down. Okay, so that's that one. Let's have a look at a couple of others. So these are just a couple of practices in converting Celsius to Kelvin, remembering that degrees C, okay, to convert to Kelvin, we are going to add 273.15. This value is in your data booklet. Okay, but it's one you probably won't need because you will be using it a lot. So 100 degrees C is going to end up to be 373.15 Kelvin, remembering our units. 175 is going to be 448.15 Kelvin, and then negative 145. Okay, so we've got 145, negative 145 plus 273. Okay, so my brain is not working. 145 plus 273, we're going to get 128 Kelvin. Okay, you need to practice these because these should come automatically. As soon as you see a temperature in a gas question, you need to be automatically converting it through to Kelvin. So let's have a look at this last example here and see what we're looking at. Again, we have this syringe example, which is a common kind of setup for gas questions. And we've been told it's 90 milliliters, which in IB speak, remembering, is centimeters cubed, measured at 1 atmosphere of pressure. So because we're using this relationship, remember the V1 T1 over V2 T2, it doesn't matter what my units are except for temperature. Okay, so this doesn't have to be in pascals. Atmospheres is perfectly fine. 25 degrees must go to Kelvin, so it's going to be 298.15 Kelvin. And we're asked what volume would the gas occupy at the same pressure. So pressure is constant, which we need for this law, and 120 degrees C. This one, again, need to, sorry about that, pay attention and convert to Kelvin. 120 degrees C is going to be equal to 393.15 Kelvin. So we have V1, we have T1, so substituting in 90 milliliters over T1, which is 298.15 Kelvin, is going to be equal to V2, which is what we're looking for, over T2, which was 393.15, remembering that we have increased our temperature, so we would be expecting our volume to increase as well. Okay, because this is a direct proportionality, not inverse like Boyle's law. And we will get, according to this, we will get 118.67, or taking it to rounding that up, so it'll be 118.7 centimeters cubed will be our final volume. Okay, so I'll leave you to do this one. What temperature would the gas need to be changed to for the volume to be 30 centimeters cubed? See how you go with that one, remembering this time we're going to be solving for T2, not V2. So we'll be solving for T2 in that one. Just a quick note, there is another law, which is the Gay-Lussac law. So where Charles came up with the temperature and volume, Gay-Lussac actually came up with a law which is much the same for temperature and pressure. So where we get this P1 over T1, V1 over T1 is equal to V2 over T2, we can also write a similar relationship for pressure, because the number of collisions that we have with the wall of the container will be proportional to their kinetic energy, which is going to be controlled by the temperature. So we can have this relationship as well, which holds true. For this one, we have pressure held constant. For the Gay-Lussac, because we're looking at the change in pressure, our volume is held constant. So, Charles' law summary. Much the same again, we need to be able to explain the relationship between volume and temperature, that being that they are directly proportional. As one goes up, the other goes up, as long as the pressure and number of mole is kept constant. We need to recognize the graphical representation of Charles's law, this time remembering that we've got V, we have V and T, and then it extrapolates back to absolute zero. If temperature is in Kelvin, it won't pass through the origin if temperature is not in Kelvin. Okay, being able to define the term absolute zero and converting between Celsius and Kelvin scales, adding to 73.15 to go from Celsius to Kelvin, and then Charles's law mathematically, which is our V1 over T1 equals V2 over T2. Okay, and that's Charles's law. Only one more to go before we can put them all together and start heading towards our ideal gas law.